Hello, everyone. So this is going to be the first part of a comprehensive review on two-dimensional vectors, so vectors in multiple directions. This is going to be the first part where we're going to be talking about adding perpendicular vectors. So to kind of put a scenario into our minds while working through this, let's say that you have just recently escaped an island by way of a raft that you've produced from these beautiful palm trees over here. Now you will be traveling at 6 meters per second, either maybe by paddling or through a motor, and your goal is to reach this stretch of land over here that looks strangely like a cucumber. Now the main catch is you've got a crosswind heading to the west. Notice I've rotated this compass over here. And that crosswind is going to mean that you may not necessarily end up exactly where you're aiming, which is just straight ahead to the north. So in order to work out where we're actually going to land, maybe as a general guess, maybe over here, we're going to need to figure out what our heading is going to be, or the direction that we will actually be moving in over time. So to get started on this, let's go ahead and separate our vectors from the picture. So we're going to start out by drawing our vectors just kind of together in the same space. So we've got our 2 meter per second upward vector right here. And it's going to be moving at 2 meters per second. And then we've got our other vector, these are not to scale, to the right, moving at 6 meters per second. Now, in order to find the resultant, we're going to have to use our head-to-tail method, as the title suggests. The head-to-tail method is very important for adding up vectors that are not pointing in the same direction, so I highly recommend you practice it. So in order to do this, I'm going to employ kind of a slight variation of the parallelogram method. So I'm going to just mirror the vector that we have over to from the head of our first vector, or the head of our main vector, to the tail of our second vector. So we're connecting head to tail, or maybe tail to tip, however way you want to talk about it. And then our resultant vector is as simple as drawing a vector connecting the tail of our first vector over here to the tip of our second vector. So this will be our resultant R, and you can already get a lot of information out of this. We now know that we're going to be moving over to the right and up a little bit, so maybe this approximate location wasn't too terribly far off. So now, this information tells us a little something about the direction, but let's say we want to have more like concrete values. So in order to find this, you notice that we have created a right triangle because these vectors are perpendicular to each other. So when you have a right triangle like this, you can use the Pythagorean Theorem, which I've provided up here. So the Pythagorean Theorem basically says a squared plus b squared equals c squared, or the sum of the square of the two legs of a right triangle are equal to the square of the hypotenuse of said triangle. So if we were to employ that here, we would say, okay, so maybe the magnitude of vector r is equal to the square root of 6 squared, which is 36, plus 4 squared, or 2 squared, which is 4. And what you get is the square root of 40, which is, I'll give you a minute. If you want to pause, you can while you run it through your calculator. And we're back, and what we get is 6.325 meters per second. Now, this tells us the magnitude of it, but we still don't really have a concrete value for the direction. So let's go ahead and find that, shall we? So in order to do that, we're going to use the second equation here, this angle equation, which utilizes the inverse tangent. Now, you'll remember that the tangent of an angle is equal to the opposite leg over the adjacent leg, or TOA, I guess you could say. So if we were to calculate our angle here, it's going to be tangent inverse of our opposite vector, which is 2, over our adjacent angle, which is 6. So I'll give you a minute to calculate that. Okay, and so what you get from that is that our angle is 18.435 degrees. Oh, I apologize for my laptop fans. Sounds like a jet engine. Okay, and so we know from this that we have officially gathered kind of our heading. And if you wanted to figure out like the heading that you should take if you want to head directly east, you could subtract this angle from the x-axis downwards, which would be 360 minus 18.35. But I think just from this alone, this should give you enough information and practice to help with these right triangle problems. And in the next part, we're going to be working with something a little more complex, something that isn't immediately a right triangle. Thank you for watching.